Today I'm just going to be classifying and solving the following differential equation. X to the fourth times dy over dx equals y minus x times y. Now, for this particular differential equation, I'm going to be using the variable separable method. Doesn't work for everything, but for this type, it will work out. I'll talk about how you know whether it's a variable separable in a second, but first we're going to talk about determining the type of differential equation we have here. Now, to make it easier to see, I'm going to write this in a different notation using primes. So x to the fourth. This, by definition, is equal to y prime, and then the rest just stays the same. Now, from here, we can look at the types. For now, I'm just going to be looking at the three main areas of concern: what order it is, if it's homogeneous, and is it linear. So as far as order goes, we look at our y's, our y primes, and if it's the first prime, it's the first order, second prime, second order, so forth. Go with the highest one. We only have y prime here, so it, by definition, it's only y prime yields first order. And it has to be, because as we see, there's no standalone functions of x. When you solve for y prime, there's going to be no x floating out without a y somewhere, or there's not a constant out here, which, by the way, if you come out with something that has, like, say 9 in it with no y's anywhere, once you get y prime by itself, that is the same as saying y times x to the 0 power. So that is a standalone function of x. Okay, now for here we don't have that, so we don't have to worry about that. So this differential equation we can classify easily as homogeneous. Forgive my cursive, this is the way I learned. It may be hard for some people to read and understand, but I'll try to walk through everything I'm doing in this video. Now, as far as linearity goes, if you look at this, the y, there's only y prime, so it's first order, and the rest of the y's, they're only to the first power. There's no, like, y cubed. So we can easily just say that it's linear. That's as far as we're going to go with classification today. Now, once you get that, for the variable separable method, you're going to have to be able to separate the original equation to where you have just nothing but x's and dx and y's and dy. From there, you can just simply integrate and find your original equation. That's considered variable separable because you separate the x's and the y's and integrate. Now, this form isn't really going to be useful for us because you need the dy's and dx, so I'm just going to copy this back down here real quick. X to the fourth dy over dx equals y minus x times y. So from here, we're going to need to get all, first off, the general guide, try to get this by itself. So we're going to divide by our x to the fourth here, which is basically just timesing by x to the negative 4, which would yield us dy over dx equals x to the negative 4 times y minus x to the negative 3, 1 minus 4, negative 3, times y. From here, we're gonna try to separate the x's and the y, so we're gonna need to get our y's back over here and our dx over here. For now, I'm just gonna simplify this so we can understand how to do that easy. bring our y's out where we can see how to get them out of there. Okay, now from here we can see all we need to do to get our y's over here with our dy is divide by y, and then for our dx we just need to times by dx to get it over here. So I'm going to write this in here, 1 over y dx, and always do it to both sides. So from there everything should cancel out nicely, which it is, and this just leaves us with 1 over y dy equals x to the negative 4th minus x to the negative 3 dx. From here we've got everything separated, that part's done. Now all we need to do is integrate, which we can because we have all x's in dx, all y's in dy. So just throw an integral symbol in there. Okay, now to integrate this part, by definition we know 1 over x, the integral of it, equals natural log of absolute value of x. It holds true for y as long as we're talking about y. So by definition, I won't go into it. There's other videos out there that'll explain it way better than I ever could, but the integral yields that. Now I'm not going to worry about the plus c that you always see with an indefinite integral, because we're going to get another c over here. So there's no real reason to have 2 arbitrary constants in there. You can just make them into 1, not worry about it. So just leave that there. Just always remember somewhere in here there needs to be a c. We're going to integrate this. We can take it in separate terms, break it up to make it easier. I won't really go into why the integrals come out. There's other ones, but just for sake of check, this is going to come out to negative 1/3 x to the negative 3rd. If you would take the derivative of that, you would see that comes out to, when you bring that down, it comes out to 1, and then you make that 1 less, which is negative 4. And then the same thing over here. That's going to make plus 1/2 x to the negative 2, and that would come out to that if you took the derivative of it. And then always remember your c. Now from here there's really no good way to simplify this. I mean, you could try, but I won't go into that right now. For now, you can just say this is your solution to the differential equation, and that's all you need to know. That's the variable separable differential equation method, and thank you very much.